Hey everybody, it's calc time again. It's Miss Wesley, and this is part two of Riemann sums, and we're still at the beginning of our definite integrals packet. We're going to actually pick up on page two, but I'm back on page one for a second. I see Squidward right up there above me, still smiling, so you get one more SpongeBob joke, and it's about Squidward. How would you make Squidward laugh? You give him 10 tickles. Tentacles. You give him 10 tickles. Can we recap what we were talking about all the way back in part one? We were trying to find some kind of weird shaped area here. There's no normal geometry theorem or geometry formula that's going to get us the area of this curved top with this almost triangular with a curved top shape. And calculus is going to get us this answer, but what we tried to do the other day was we tried to just approximate the area between this curve and the x-axis by using a shape that we know and love that's easy to get the area of by using some rectangles. And we decided on four rectangles. Four rectangles where their endpoint, their left endpoint, fell along the curve. That was an underestimate of the area. We added the areas of four rectangles where their right endpoint hit the curve. That was an overestimate of the area. Even averaging those areas got us a better estimate. And making the midpoint of each rectangle a point that was on the curve actually gave us an almost accurate picture of what the area would be. We are so close. We're all around it. And I'm wondering if you're guessing what the actual area is. It's a number that you should recognize, but let's actually find it. Today we kind of just get rid of that suspense. So I'm looking at page two, and we started connecting this back to an early calculus concept of a limit. A limit as n, the number of rectangles or the number of subintervals for these rectangles approximating the area below this curve, between the curve and the x-axis, as n gets bigger and bigger and bigger. You can see, if you look at this picture at the top of page two, can you see that if I took the areas of all these rectangles that are here and I added them all up, I'll shade them here, that it would be a pretty good estimate, but not 100% accurate. I see there are times, because this curve kind of changes concavity throughout the way that it goes, you've got some little chunks of space that are missing, underestimating, and then you're kind of counterbalancing that with some overestimates that are above. Well, how much more accurate is a picture when you have, let's say, 24 skinny rectangles? If I added up the areas of all these 24 rectangles, it would just be so much more accurate. And calculus says you need to figure out a limit of these sums as n approaches infinity. Imagine an infinite amount of rectangles, or even better, trapezoids, beneath that curve, and adding together the areas, you would have such an accurate picture of the area under the curve. So let's put some calculus into this. Let f of x be continuous, there's no breaks in it, and it's above the x-axis on an interval from x equals a to x equals b. And the way we can write the region under the curve's area is we can say limit as n, the number of subintervals, goes to positive infinity of, now think of what we did on the last page. We were multiplying a width of each rectangle. So the delta x, I'm going to call the width of each rectangle. Let's say rectangle width times the sum of all the heights, right? The sum of all the lengths, since we know that rectangle area is length times width. And how do we get the lengths? Well, we use the original function. We plugged in f of each endpoint there. So f of the first endpoint, the first height, f of the second endpoint, the second height, all the way up till we got to the nth endpoint. So f of x sub n. And these are going to be the heights of all of the rectangles. So I'll put that here. So we could say maybe lengths of the rectangles versus width. That's there. And that is going to give you the area. There's a special name for this type of sum of a bunch of rectangles or a bunch of trapezoids. We just haven't covered that. It's called a Riemann sum. Riemann sum. And now we're going to take this a step further. I am not interested in having to do every single one of these area problems like we did on the first page with these approximations. So that's where a definite integral comes in. The definite integral, right, of the function f on the interval from a to b is the limit, we're going to say, of the Riemann sum as n gets bigger and bigger and bigger, as n goes to positive infinity. That is how we can write this. Is we can still use the integral symbol like we did with indefinite integrals, but we're putting these limits of integration on the top and bottom. We're going to put an a down here, the lower limit, and a b up above the upper limit. We're still integrating the function f of x, and we still get that dx notation with it too. Every integral has it. You're integrating with respect to x. But the new part for us and what makes these integrals definite is you have a lower limit. I'll put that first. Lower limit, I have to spell that right, of integration is going to be the value a, and then you have an upper limit of integration, basically giving you boundaries. We're going to learn over the next few days of the unit that indefinite integral can actually give you a really good value for the area under the curve. We'll get there, but it's not the whole entire curve. It's just from point A to point B. Do I have another picture up here? This is just, we weren't interested in the entire curve as it goes to infinity. We're just interested in the area between those two x values from A to B is a way you could write it. And it's just the limit of the Riemann sum times the width of each rectangle. Actually, we had a picture right down here. Area under the curve. As long as you have a continuous curve and you're above the x-axis from A to B, the region under the curve has an area given by this definite integral. We're just going to write it once again. I'll say capital A for area equals the integral from A to B of f of x dx. So this is going to lead to some cool types of questions. Let's flip the page. The next page is some practice that I wanted you guys to try with just these estimations to get an idea of what this integral is telling us before we just have it spit out numbers for us. So if I try the first one's kind of a good one to start with because it is just a linear function that we should be able to handle. It says, can you find, we're going to use 4 subintervals, and we're going to use rectangles with left-hand endpoints. And we want to just make an estimate of the area between this line and the x-axis. So this line we could graph, right? This is like saying negative 2x plus 3. You are up 3 for a y-intercept, and your slope is down 2 over 1, right? Down 2 over 1. And I could go this way, up 2, I'd have to extend that line a little bit, and I get this picture here. Almost missed a couple of those dots. And we specifically care about the area between negative 1 and 1. So I'm going to draw that here with a couple lines. I want to go from negative 1 all the way up to 1. So x equals negative 1, x equals 1. I could shade this area in here. Now, it's kind of funny because we have a formula that could get us this area exactly. Let's see what a Riemann sum would get us. I want to make 4 rectangles with left endpoints on that line. So let's draw it first just to get a sense of what it should look like. Left endpoints. So I'll start here. And 4 subintervals. If you split 2 units up into 4 parts, each unit is, or each rectangle would be half a unit in width. So your first rectangle is going to come down, be a little bit of an overestimate, but its left endpoint is going to be right on the line. Whoops, get that back in there. Okay, the second rectangle, have your left endpoint be on the line, another little bit of an overestimate. Put that there, that is a little bit tricky. Okay, third rectangle, left endpoint, have it go over to x equals a half. And move that back up. And last one, last rectangle, left endpoint is going to be on the red line. Left endpoint would be there. We'll estimate it this way. Okay, maybe the picture's a little confusing. Let's actually write it out and see if we can do the math here with adding together the area of 4 rectangles. Here's the notation. We want the area, I'll put capital A for area, from negative 1 to 1. We can use those as your limits of integration of f of x. So I'll write what f of x is. 3 minus 2x taken with respect to x. This new notation with the little number above and below the integral sign means you just want the area of the curve from this x value to that x value. Let's try it with a Riemann sum. So we want area to be the width of each rectangle. So here we split up 2 units into 4 parts. The width of each rectangle is a half a unit, so 0.5. Then we want the heights of all the rectangles with left endpoints. So we'll start with the first height being at f of negative 1, the first number. And we need 3 more heights. Each of these x values is going to get a half a unit added to it. The next rectangle is the height of f of negative a half. We're going over a half. Plus the height when x is 0 would be the next one. And I think the last one would just be a half, 0.5. All of those numbers that I decided on for those x values are the left endpoints of each of those rectangles, each of those 4 rectangles. Now it's up to the calculator to do a little bit of work for you, and maybe some of this we could do on our own actually. Maybe I don't need the calculator too much. So 0.5, if I plug a -1 in here, I guess I shouldn't need a calculator. 3 minus 2 times -1 is just like saying 3 plus 2. Your first height should be 5. The next height is plugging in a -1/2, so 3 minus 2 times -1/2 is like a 3 plus 1, and our second height I think should be 4. F of 0 is 3, and f of 1/2 is actually 2. So our approximation is 1/2 of, I think, 14, right? 9 plus 5, so 14. And we're approximating 7 units squared. I'll pretend like I meant 7 the whole time. And I'll put a question mark by it. Was this the best way to do this particular problem? Do you think this is an over or an underestimate? Well, if I look at the way I sketched this picture, definitely an overestimate. We've got these extra chunks of area that aren't included under the curve. What would the real area be? If I just took the area of this trapezoid, right? This is an aside. We could actually check it. Area is the average of the bases times the height. So if I average 1 and 5, 5 plus 1 over 2, multiply it by the height of that trapezoid, which is a 2-unit height, you get 6. The actual area, and this isn't necessary because we're just approximating today, but the actual area would be 6 square units, whereas we got an overestimate using the rectangles. I think the rectangles will come in more handy as we look at the next few questions, and I think number 2 would be a good one as a follow-up. So now we're talking about a curve, and you have to think about your knowledge of graphing when you want to sketch this. Of course, you can use a calculator to help, but we know a thing or two about this function. What would the shape of it be? Well, 1 minus x squared. That looks like a parabola to me. It's -x squared, so it's going to open down, and it's going to be up 1 unit. So I'll put 1 unit way up here, and it's going to open down this way. So that'd be a good little initial sketch. And we actually only care about the right-hand side of this parabola. We care about the area from 0 to 1. So from 0 to 1, we need to make 4 rectangles, and they are each going to hit the curve at left-hand endpoints. So 1, 2, rough sketch, then 3, and then 4, like that. Again, we're going to get a slight overestimate here, but here's the notation we want. We want the area from 0 to 1 of 1 minus x squared, taken with respect to x. And let's use those 4 rectangle areas. The width of all the rectangles, I think in this one, it's you're splitting 1 into 4 quarters. So each rectangle would have a width of a 0.25, the way that I sketched it. The height at the left endpoints, your first one's still 0. F of 0, f of, now can you only travel a quarter? So f of 0.25, f of 1/2, 0.5, and then f of 3 quarters, 0.75. Okay, give that a try, right? The calculation, you can always pause the video to do the calculation. It's a quarter, and then you have to take each of these x values back to the original function. So 1 minus 0 squared just gives you 1, but then we're going to have some approximations. 1 minus a quarter squared is going to give you about 0.9375, slightly below 1. 1 minus a half squared will give you exactly 0.75. And then 1 minus 0.75 squared gives you 0.4375. Don't mean to rush this, but pause, add these all up, you get about 0.78 units squared, 0.78125 units squared. And there's your slight overestimate, but it looks like it makes some sense. It wouldn't be a whole unit. It's close to a unit, but not quite. I want to skip down to number 3. It says y equals 1 over x. 1 over x is a hyperbola. It's going to have asymptotes. It'll have, I should draw this in, it'll have a VA, a vertical asymptote, at x equals 0, and it has a horizontal asymptote because it's bottom heavy at y equals 0. There are some pretty easy points you could plug into it as well. 1 is an easy point to plug in. So if I plug in 1, I get 1 back. And this part of the hyperbola branch is going to curve down from there. To get you started on this, you care about the area from 1 to 2. So I'll put 2 on the picture as well. And you want to make 4 rectangles with left-hand endpoints. So 1, 2, 3, 4. Then again, not meaning to rush it, I'll just write this before I go. You're going from 1 to 2 of 1 over x dx. You want each, 0.25 is still going to be pretty good for the width of each rectangle, but you want f of 1. This is f of 1.25. You'll have 1.5 and then 1.75. Try the calculation, check your answer with my key. I hope you guys have a good day. Stay tuned.